So 1 over t, and this should give us the average value. And that's how you can calculate the average value or the mean value of your signal.
So in the integral quarters are the beginning and end of my signal.
Yeah, and this we still need some borders. For here, it's T0 to T1. So, in order to get our average value of the signal, our signal must be a periodic signal. Because otherwise we cannot get the period, and we cannot get the lower and the upper border for our integration. Yeah. And now we can try that for our sinusoidal function. It's quite simple, we only have to put in our equation here. So it's 1 over t, 0 to t, because we can set our integration border t0 equal to 0 and t1 is actually t. And the function equals to x peak times sine omega t dt.
We don't have to put phi. Yeah, it's only one wave.
What is only one way?
A wave, I would say. Because it's WT plus omega t plus phi. That's it. It's
We
one
don't
signal,
need
I'm
phi
sorry. Yeah.
because we
Yeah,
are
it's only signal.
assuming that we are starting
Yeah,
with
from 0.
t equals 0 and the signal is 0 here.
Yeah.
So it's actually xp over t times 0 to t sine omega t dt. What is the integral of the sine function?
Cosine.
Cosinus. So it's minus xp over t times cosine. Now we have to calculate the upper and lower border. Did we forget something? Or is it correct?
A constant.
Plus c, the constant. That's not what I'm referring to. But if you are integrating, we are integrating with respect to t. But our argument is omega t. So what do we have to
Omega is
account for? The inner derivation. Yeah? If we are doing a derivation, then you multiply with the inner derivative. If you are integrating, then you have to divide by it. That means we have to divide by the derivation of our argument here. What is this?
So it's cosinus divided.
If we are, our derivation is with respect to t. What is this? Derived along t? 1.
You want to
So
substitute
it's
something?
omega t
Is equal to
derived with respect to t What is this?
Omega.
It's omega. So we have to divide the whole thing by omega. Here. What is the cosine from omega t?
We really need to look over the mathematics because we forgot.
But we will try to solve it now.
We don't have to wait.
So can we calculate if the argument is omega t, the cosinus function? Normally we got an angle as an argument. Huh? Is this an angle or what is omega t?
Omega is, you said it's an angle. It's
Omega
also-
is the angular frequency.
Yeah.
Angular frequency. And frequency is always related to period. Huh? So we have to think about that. Let's stick to the other one. So omega is equal to 2 pi times f. And omega t is 2 pi times f
Times
times t. What is t?
1 divided by
T is 1 over f.
So it's 2
So
by
this
t.
is equal to 2 pi.
Yeah, 2 pi. WT.
So omega t is the angular frequency. For one period, it's 1 whole second. So it's 2 pi. And this will ease the mathematical problems.
Yeah. 2 pi t cosine 2 pi t.
I have a question about the omega, which we added to this.
We divide it.
Yeah, we added to this equation. So for the first time, we don't need it, but from where this appear?
This is the inner derivative.
Differentiation.
What do you mean by it?
Let's see here. If you're doing your integral sine x, this is minus cosinus x. Huh? But now but for x, dx derivative relative to x is 1. So all the time actually we have divided by 1, but normally we'll write this down in that way. So you
I
forget
understand.
about 1. This is here all the time. But now we got a integral sine omega t. This is the same.
Yeah.
It's minus cosinus
Yeah.
omega t. Because we are treating the integration that this is a unity.
Yeah.
But then we have to divide by the derivation of this unity. With x integrated along x, it's 1. But with omega t integrated along t, if you derive omega t, omega t relative to t or along t, then it's not 1, it's omega. So you have to divide by omega here. Yeah? So now it's getting a little bit simpler.
Cosine, yeah,
Because we got x p
minus 2 pi.
divided by 2 pi times, here we missed the brackets, cosine of 2 pi minus cosine of 0. What's the cosine of
2 pi
2
t.
pi?
Yeah, WT
30
also. Yeah.
degrees.
360.
Yeah.
Minus 1? 1. So 1 minus 1?
0. It's all 0.
0.
So
What
we
gives us the
can
instrument?
0.
And that is actually what the instrument does. You see, it's a simple of integrating. This
To
small
get them.
instrument can do. But actually, with the old instruments, with the pointer, it was a matter of mechanical, what do you call this, Drehkeit. Forget.
Okay.
For the books, Drehkeit. But with the electronic instruments, it's just a simple integration with a capacity. The capacity actually does the integration. Yeah.
The integration of the conversion, but that's not
But you can ask Mr. Semyonov to give you further details of this inner derivative.
Don't think so.
The thing is that I know, I can remember so vaguely, and I know I have my notebooks with me, and it's not easy, because we do this at school, but I didn't do them for 3-4 years, so now I'm
6
blank
years for
memory.
me. 6-7 years.
But this is the easy part of the game. Huh?
Yeah, of
If
course.
we're doing the RMS value, it's a little bit more tricky.
We don't need to, I think.
Will we
We
have
don't
this
need to.
stuff?
I'm asking.
What's the time?
It's 2:12.
Time for a break.
Fits in 12.
Okay. What in 12? But then you're quite right. We will skip the RMS value and we'll go on with noise.
We have minus at the end. Continue? Yes? No.
Yeah,
Minus
here we
we
got
got
minus.
minus.
But since it's zero anyway,
So it doesn't
we
matter.
don't care about it. But we are doing another example that will not give you zero, because it's rather boring if we have as a result all the time zero. Right? And what is going on if you change in the instrument to AC? Why do you get the value then?
Yeah.
This we will do in the next example. 'Cause
And why
the
we
inst-
get the question? Sorry, why we got 220 volts, but we and here already 320. Where is this 100?
That's the problem with the RMS value. Huh?
Okay.
What is RMS? RMS stands for root, means square. What does that mean? That's actually the operation you need to calculate the RMS value. And why are we always interested in the RMS value? That's the question. Because you can't forget about the average value. You can't forget about the rectification of the signal. But since the beginning of electronics, everyone was interested in the RMS value. Why? Any idea?
More accurate?
More accurate than zero?
No.
Hard to do. But normally think about the ancient times, not Stone Age, but around 1900. We are talking about telephony systems. So that was the broadest application area of electronics. So you want to have a telephone call from Rome to, don't know, Helsinki,
Vienna.
whatever is the distance. Actually, it was invented in the United States. So there were telephone calls from east to west coast. And all you are interested, if you are talking into that microphone, what kind of power will be transmitted to the remote speaker. So all the things where we are interested in power. For a DC signal, it's quite easy. Well, for a DC signal, behind. Go here. Leg side up, so. For DC signals, it's quite easy. For DC, let's say we have a 12-volt battery. How can we calculate the power? It's U squared over R. Let's say we connect the resistor to the battery. And we would like to calculate the power that is transferred to that resistor. So we can calculate the power U squared over R, or V, what you would like better. But what happens if we change our DC source to an AC source? And if we are talking into the microphone, the signal is not a DC signal, the signal is an AC signal. So it's an alternating current signal. AC, how can we calculate the power? The relation must hold true. So it's V squared over R. But what kind of V? Or voltage. So what kind of voltage? If we are thinking about this sinusoidal signal, what kind of voltage setting should we use? The peak value? 0? 0 is obviously wrong. Huh? But the peak value?
An average?
An average?
No.
The average is
Zero.
Each time you have to calculate the effect time.
value.
Because it's difference. So
because if we are taking the peak value, that's wrong. It gives us too much power.
Yeah.
Huh? So actually, the measurement, the way of measuring this in the early days was done in a way that we have a small resistance here, and we are checking the resistance for getting warmer. And out of the amount of heat that was produced by this resistor,
But why it's compulsory to have the positive peak value the same as the negative peak value?
because for every technical sinusoidal signal or main supply, the peak value, the absolute value of the peak value is always identical to the negative.
Like it's a theorem, or like we just have to accept it like this, or
Yeah.
okay.
Other way, how can you generate such a sinusoidal signal? Take an easy example. Take a pendulum and monitor the excursion.
Yeah.
And you will see that the positive peak value is always the same as the negative peak value.
It's a fact.
So that's also the electronics stick to that. Though with the modern generator you can change this. You can set the offset, and then you set an offset. To take another color here. You can set an offset, maybe 100 volts.
Like what we did in the...
Like we did in the lab, and then the positive peak value is different to the negative peak value. That's why we never refer to the positive or negative peak value. What we are doing is the peak to peak value, because this stays the same.
Yeah, so
With or without offset.
we actually didn't change anything, I think.
Yeah.
Because
Okay.
it's... Yeah,
So it's a
right?
way.
Yeah,
But
because...
if you have to change something, it's easier if you are knowing what's going on. Yeah.
Because what I mean here, we changed it from 0 to 100. It's
Yeah.
the same. If I just
In
shifted
the lab, maybe
yeah.
we changed it by 1. If we got a peak to peak of 5 volt, we changed it by 1 volt.
Not I mean we changed it from 0 to another value, so we didn't change anything. We just shifted the axis. Right?
No,
yeah,
I
but
don't
shifting
think
the
it's not
axis,
zero
this
there.
is setting an offset.
Mhm.
But if you make the normal average, like normal mathematics, it will not give you 0, the average.
Of a sinusoidal function, it will give you 0 as average. Except you got an offset. Here. We can introduce an offset here. Then this will be the offset. This will be 0 and the average value will be the offset. That's clear. But normally we use an offset-free sine wave. Yeah. But here we got the problem. What kind of voltage reading do we have to fill in this relation so that we get the right numbers? We can measure it, go to the thermal energy that is generated in the resistance. And after a long research, it took 10 to 15 years, they were coming up with the RMS value. Yeah? And if you knew the RMS value of your signal, then you just put it in here in the formula and you got the correct readings for the power. So if we are talking about power, you always have to use the RMS reading of your signal to calculate the power. And that's the fundamental importance of the RMS value. So normally, if you have an AC signal, you all the time state the RMS value. Yeah? Though it's pretty complicated to calculate it. So if we want to calculate the RMS value of our signal, and let's stick to the sinusoidal signal, it's calculated by, here you got the root.
Yeah.
So it's the root, the square root,
Yeah. Mean.
the mean,
1/t for
And
integration. Yeah.
squared.
Second.
And the integration goes from 0 to 1.
That's the same now. 0 to t
Yeah. T is
To t.
over the squared signal and relative to t. This is a little bit more complicated than
yeah.
the average value,
A little more.
a little more. But we will skip that.
Okay.
This we will do at the test.
That's a bit okay. It's recorded.
Okay, so but the important thing is, if you knew the average, the RMS value, then you calculate the power the signal is generating. And that's the important fact. We do not the derivation, I give you the result. RMS value equals the peak value divided by square root of 2. Yeah.
It's just peak.
X
Not peak,
peak.
peak.
X
Peak.
peak. So the amplitude of the signal. We are assuming an offset-free sinusoidal signal. We normally never use an offset. Because if you have an acoustic signal, there is no offset with that signal. If you got a light wave, there is no offset. Okay, since time is running out, we are skipping the rest of the deterministic signals. You can look it up in the script anyway. There you got the derivation of 1 over square root of 2. Go for it, and if you got any questions, then you can ask me the next time. And we will focus on the second part. First was deterministic signal.
And the
The
noise.
second part is stochastic signal. Or noise. Get a new pen. You see, due to the pen, more than 3 hours it's not possible. There's only 1 pen per hour. So, everyone is familiar with noise, radio or television. And the most important thing is that we cannot avoid noise. So we cannot generate a technical signal
Without noise.
without the noise share. So that's why these signals are more important than the deterministic signals.
Because we
Because
can
they are-
control it. The other
We
one.
cannot control it. The deterministic signals we can
Yeah, that's what I
control.
mean.
But noise, we can control it with the circuit design a little bit. Yeah? But most of the noise share is given, depending on the application and the setup. So as I told you before, there are 4 mechanics. One, it's thermal noise. So thermal noise, as the name implies, it's related to temperature. But not in degrees Celsius. It's
Kelvin.
related to Kelvin. Huh? And you can only omit thermal noise if you cool down your apparatus to 0 Kelvin. And as we had before, this is technically not possible. Yeah. So in other words, we cannot avoid it. Where does it stem from? Here we have to get a little insight into our conductor. What do we have in our conductor?
Atoms.
Atoms. On a very small scale. We see the atoms. And normally the atoms is a sphere. You can imagine how it's going on. And now, if we got an electron, or let's say we got a huge number of electrons, and they are moving like a front. So this is the ideal setup. It's another thought experiment again, yeah? And there are the atoms. And this front is moving with a certain speed. V electrons. And all the electrons are moving synchronous to each other. So it's more or less the front of a wave. And they are drifting into that wire. So what do you expect to happen? Will you see the front at the other end of the wire? Yeah?
It's a
No.
short circuit. No?
It's a short circuit? Yes, but we are thinking about the wire. Maybe the load, the resistance is somewhere else. This is just a piece of a wire.
Yeah,
But you are quite right, the wire is normally a short circuit.
the atoms will absorb the electrons and emit them, and then it's radiation and it's noise.
It's not that catastrophic. It's a little bit easier. So this front is moving through the atoms. The atoms will, let's say, the atoms will not absorb. There might be some electrons that be absorbed by some atoms and emitted afterwards.
That's
But
why
for-
it's become warmer. Okay.
Yeah. But for now, let's say it's not that critical. But what will happen? If you're following one single electron, it will not move straight. But there might be one electron that moves straight to the crystal, to the other end. So this one is the first. If we are counting the electrons here, then we will have a certain instance of time. We will count, let's say these are 10 electrons. Yeah? Then we will count 10 electrons, and for other times it's 0. Yeah? And these electrons move through the crystal. And there is one lucky electron that moves through the crystal without colliding with the atoms. Yeah? But more probably there will be one that collides with the first one. And will come to the other end. But obviously it takes longer to get to the other end. Huh? So at the other end, if we are doing the same electron counting, we will have one period of times with, let's say, 5, 3, 2. At the end we will count also 10 electrons. But related to time, we will have an instance with 5 electrons, and instead of time with 3, with 2. If we are using much more electrons than 10, this distribution will get smoother. You will have this Gauss distribution. At the end, we will see the same, because we got our ideal setup that all electrons will enter at the same amount, or at the same instant of time, into the crystal. So what we will see, that these electrons will drift apart. And that is also, if you're transmitting an impulse over wires, this impulse will drift apart. That's the same problem. Yeah? At the output, we will see that distribution. And if we are monitoring this distribution over time, so here we got a step, we got a higher current, that's it. And here, at the other side, we will monitor an average value of the current, and we will have some deviation from that average value. The signal will look something like that. There will be an average value. We knew about the average value. The average value is our DC reading. But if you are taking an oscilloscope and monitoring your current or voltage, with voltage the same, you will see that it's not a straight line. Yeah? Due to the noise, it got more or less fuzzy around this mean value. So what you will see is some kind of waveform you cannot describe, and the important point here is you cannot describe this waveform on a mathematical scale. It's randomly. Yeah? So the number of electrons you will measure at the output, it's a random function. Yeah? So you cannot say, are you here? So the measurement instrument will go through this and will give you the readings for the different intervals. And each interval will give you different readings. Yeah, if you got a bigger ensemble than 10 electrons. Huh?
Excuse me, how we can reach from that diagram to this one?
From that to that? This value in the middle, it's the mean value. This will give you this reading. And the deviations from that mean value is in this area. Yeah? So actually it's much more complicated than that. But if you're taking an instrument and measuring the current at that end of the wire, then you will, maybe you are measuring 10 electrons, 15 electrons, 13 electrons, 14, 18, 9, 17, and that on. And the mean value of all these measurements will give you that value here. Huh? But as you see, for different instances of time, the actual value is quite different. And this will give you the actual reading of your instrument. Huh?
The highest one.
So it's a statistical problem. So that means on this side of the wire, we cannot state the exactly numbers of electrons that we will measure at some instance of time. We can only state a mean value, yeah? But we cannot state an exactly number, because we don't know how long it takes for the electron to get through the wire. Yeah? And that's what we call thermal noise. And this has account for the different paths through the crystal. Yeah? But we can state the mean value, the average, because the instrument will definitely give us some reading. And this is not only related to AC currents, it's the same if you have a battery. Yeah? We take a 12-volt battery and have let's say we have a bulb here, and we put a measurement instrument in here, and let's say it's an instrument that can measure the number of electrons, a theoretical instrument that can measure the number of electrons in very small amounts of time. And then we monitor the reading, something like that, and if we draw a graph, then our readings, we can put in the readings here. This is actually the reading. And what the instrument will give us, after all, is the average of all these readings. This you have to understand, that actually your measurement results is all the time an average. It's not the exact numbers on the current, because every time you got stochastical signals involved, you cannot state the exact value of the current.
Because it's randomly.
It's randomly distributed.
Okay.
The only thing we can state is an average value. Yeah? This we can also draw. You can also draw some other diagram. Let's say we collect our measurements of the different time slots for a long time. And then we do a statistic across all these numbers. Then we can say, for example, the number 19 amps, let's say, was available 50 times. Yeah? So all these numbers we collect for a long period of time, and then we do a probability distributional function. So we state here the probability for seeing one special value. And if we are doing this, so we just collect the numbers and count how often they are measured and do a distribution over this probability, then we will see also this Gaussian distribution of the values. Here in the middle, it's the most probable value. this is the value that our instrument will give us if we are setting for DC. That's the average or mean value. Yeah? And if we are going down here for, I think it's 71% or 69, something like that. You have to consult your statistics teacher. I guess it will be Mr. Silvanov as well.
Again.
Huh? And if you're, it's 1 over square root of 2, I think. And this is 0.71, so it's 71%. It's 1 over square root of 2. And in this distribution, then this here, the standard deviation, will be exactly the same that the instrument will give you under the AC readings. And this is defined as the RMS value of the noise signal. Yeah? So this is actually, because here it's not time, these are the different readings. Yeah. Do you understand this curve?
No, please explain again.
Okay. So we're doing our, let's say this is only an theoretical experiment. Yeah? We have an instrument. Let's say the instrument measures, give us one value each microsecond. Yeah? And it counts the number of electrons, for example. Yeah? At the first microseconds it counts 10, at the second 15, at the third, so that's always the values for 1 microsecond. Yeah? This gives us a huge number of, a huge lot of numbers. And then we do a statistic over that numbers.
Get the average.
We are seeing the number 10 maybe. The number 10 we had 40% of the time we had number 10. Then we had number 11, number 9, and so on. Out of these, and each number is representing the number of electrons per microsecond.
These are the deviation.
These are the deviations. Eh? Then we had 12, we had 8, 7, 13, and the farther it goes apart, the lesser the probability for that number. Eh? And here we can draw a curve. And this is the Gaussian distribution, but some kind of curve. And the most probable value is the mean value. It's defined as the mean value. It's the value in the middle. And if we go down from the 30% probability by a factor 1 over square root of 2, that's the standard deviation, normal in statistics. This value, apart from the mean value, is defined as the RMS value of our stochastic signal. Because for the stochastic signal we cannot state an amplitude, because the amplitude is changing all the time. You can try this with your oscilloscope, increase the resolution, and you see that this will go apart, and you cannot see a curve, and you cannot have a measurement value. This is obviously randomly. The exact number per microsecond is obviously randomly. Yeah? But if we're drawing a distribution over all of this value, then we got a mean value, and we got a deviation from that mean value where the curve goes under 1 over square root of 2.
You wrote 40% or 50% on the top of the.
40%.
40%.
So we have to.
But that's an arbitrary number.
Okay.
That depends how flat this curve is. Yeah?
Okay.
It might also be you have only 20% of these readings
Okay. That
is
is
the
why.
mean value.
And we have to
So there are
multiply by-
different distributions depending on the kind of noise. It might look like that. Yeah? So then it's obviously more than 50%. But there's only one thing, the area under the curve
It's always 50.
must be always 1. Because one of the values must be one of them. Yeah? So depending on how broad this distribution is,
Was
the peak
100.
value is higher or it flattens out.
Does that mean we lose the part above 1 divided by a square square root of 2 by the noise?
No, that also means different, if you got different noise, if it's noisier, then it gets broader. If it's less noise, then it gets smaller. But if it gets smaller, then you also see that this RMS value of the noise signal is smaller,
Yeah, then we have
less noise. So here it's 1, and we go down to the value of 1 over square root of 2. Yeah, so this is 71% of the peak. The peak is 100%, we go down to 71%, have a horizontal, and here we are cutting through that distribution, and this value from here to the mean is the standard deviation, and this is defined as the RMS value of the noise signal.
So it's exactly the same as the positive one, but as a negative.
Yeah, this is symmetrical for both sides. And if we knew the RMS value of the noise signal, then we can calculate noise power. Then we can calculate the power of our noise signal. And for thermal noise, since this is only a matter of thermodynamics, the warmer it gets, the spheres of the atoms will blow up. So the warmer it gets,
The more noise
the more probability for colliding with these atoms,
is more.
the more noise we have. So this formula is referred to Boltzmann and gives you the power of thermal noise. It's KTB. K is the Boltzmann constant, T is the absolute temperature, and B is the band wide.
What is band wide?
What is band wide? That's another, how many minutes are left?
10,
10?
10 to 15, 50, what?
Well, we were supposed to have a break and we
Yeah.
didn't have it, so how many minutes do we have to take
I
off?
think if it's 3 o'clock, then it's finished.
Okay, then 10 minutes, 11 exactly.
Okay. So,
TikTok.
Always symmetric or
the curve is always symmetrical to the mean value. Yeah? It's not possible that one side will look like that and the other will look like that. Yeah? That's not possible.
And how we can get to that 1 divided by the square root
This is
of
a
2?
definition.
So we have to multiply a 40% by
No,
this.
forget about the 40%. This was always an arbitrary number.
Assumption.
That depends on the wideness of the curve. Because the smaller we get here, the more values must be equal, and the more values will, and the more of you will see the mean value. Yeah?
Yeah, okay, so for example 50% or 20%.
Yeah, whatever.
Where is
So
the place
this-
of that 1 divided by square root?
This we define as 100%,
Okay.
Then we go down to 71%. 71% is actually 1 over square root of 2. Yeah? So 1 over square root of 2 is 0.7172 something. But you can do the calculation, I think it. And then the horizontal, where it cuts with the distribution, will give us the RMS value of the noise. And Boltzmann found out that the power can also be calculated. It depends only on the absolute temperature. And then we have the bandwidth. So that's the problem. Why do we have the bandwidth in here? Then we have to look at the noise signal from a different perspective. So, let's say we have only a pure AC signal, only a noise signal. It might look something like that. No matter what you are drawing, it will be correct. So over time,
we will know.
And if we are doing a spectral analysis of our signal, how can we do a spectral analysis? So if we are getting the spectrum of our signal, we're doing a Fourier transform. Must not be fast, can also be slow. Then we have the spectrum of our signal. So it's frequency. And if we are monitoring here the energy, so what we are interested in is how is the energy distributed over frequency. This was the probability of a certain readings over the readings. And here we are monitoring the energy distribution over frequency. And if we have a distribution over frequency, that's what is called a spectrum, or a spectra. Yeah? And if we are doing that for thermal noise, then we see that's evenly distributed. So the energy is equally distributed over all frequency. Not mine, I think. Oh, it's not Okay, so the energy is equally distributed over all frequencies. That means that if we would like to calculate the energy content of our signal, we have to apply a lower border, lower, and the upper border. And the energy is given by the integration from the lower to the upper border over our energy distribution over frequency. Yeah? What does that mean? And the difference between the upper and the lower frequency border, that is our bandwidth. Yeah? That means the wider the bandwidth is, the more noise we gather, the more noise energy we will have, so the noisier it will get.
Yeah, the more energy, the more noise.
Yeah. But that there are noise signals that have a completely different distribution. For thermal noise, it's an equal distribution, and that's why it's called white noise. Why white? Why not blue or yellow? there is blue noise,
There is blue noise.
there's also red noise and brown noise
Why?
and
Why?
pink noise.
Really?
Really? It's not a joke.
That's not a joke. Okay. I thought it's a
Wanna
joke.
make an experiment with the pink noise?
The major difference of the white.
So white light.
Yeah.
What is white light?
You
Is
said
there
there is
white light?
nothing with white light.
Observe.
You said that
If
that's nothing.
if the energy is distributed evenly over the frequency, then the human eye
We'll see it in
will
white.
interpret this signal as white.
Uh-huh.
So actually you knew it from the monitor. White is red, green and blue. If there is only a single diode active, then it's red, green or blue. And if all three are active, then it's white.
Mhm.
And that's why we also call it white noise. For the human eye it's a little bit different. Yeah, it's from 400, as we have said. 400 nanometers. This is nearly ultraviolet, down to 800 nanometers. Below 800 or up 800 nanometers is infrared. And here it's ultraviolet. And this is the visible range. And the sun, the energy distribution of the sunlight is something like that within that range.
So es
Ja?
ist noch optical signal, oder?